Alright, what's up everybody? We're going to be focusing today on one of the more difficult topics that you can focus on within discussion on trigonometry. And that's still continuing with the sine rule, but it's going to be what's called the ambiguous case with the sine rule. The goal here is that you're going to be able to find all possible solutions of a side-side angle triangle using the sine rule. Now, this ambiguous case thing, I said that it's very difficult. What we're going to do is we're going to give it kind of a cursory inspection. We're going to discuss it just very superficially. I'm going to try to make sure you know the highlights. What we're doing, you could go way more in depth to, and there's a lot of rules you'd have to learn. All right. I think if you focus on what I teach you, though, here, you're going to understand enough to be able to succeed in any IB-related ambiguous case questions. Okay, now, we need to talk about several things here. One of the things is that the other day when we were talking about, well, in another video, when we were working with the sine rule, we said there were three types of triangles that you can solve using the sine rule. You could solve either an AAS, an ASA, angle side angle, or SS, A triangle. Okay? And so we're focusing now on the situation where you've got side-side angle triangles in particular. Now, part of what we're going to have to discuss here is going way back to geometry. You might remember, for instance, that if you have any two triangles that have two congruent angles and a pair of included sides that are congruent, that it automatically makes those triangles congruent. So, for instance, if I asked you to make a triangle that had a 70-degree angle, then a 3 centimeter side joining it to a 40-degree angle, every triangle you try to make with those three measurements is going to be exactly the same size and shape. That's not the case for a side-side angle triangle. All right? If you're ever given two side lengths and a non-included angle measure, sometimes there's more than one triangle you can make with those measurements. Now, I'm going to try to explain this to you. Let's just say, for instance, that we have a triangle ABC, and we're going to say that angle A is 50 degrees. I'm going to say that side A is 7. I'm not going to use centimeters or meters or anything. I'll just say it's 7. And I've got a side B that is equal to 8. Okay. Now, it's really tricky trying to draw a side-side angle triangle because without knowing the two sides that form an angle, you're trying to draw an angle without knowing both of the sides. Here's the way that I'm going to do that. I'm going to go ahead, you see I've got a kind of a dotted line that has an indefinite length to it. I'm going to say this is going to be one side of my 50-degree angle, and I'm going to put the vertex of that 50-degree angle right there. And then I'm going to go ahead and make kind of a 50-degree angle. So we'll just pretend that is 50 degrees, and we'll also pretend that that is 7 units long. All right, 50 degrees, 7 units long. All right, then, oh, you know what? That shouldn't be the 7, that should be the 8, because the 7 has to be across from angle A. I'm saying that's angle A, correct? So let's say this is side B, and it's 8 units long. Well, now, I'm trying to make another side, and it would have to be the side kind of over here, 7 units long, right? Now, I'm saying it's got to be a side over here because the side that's 7 is side A. It's got to be across from angle A. And it turns out there's a couple different ways that that can happen. Watch. Pretend with me that the radius of the circle that I've drawn is 7. And that's, you can see it's a little bit shorter than the 8, can't you? That will help you see why it's possible to make two different triangles that have the sides 7 and 8 and a 50-degree angle that's not included. One way that I can make that triangle is to go ahead and connect this side to right here, okay? That would then have a length of 7, like what we're looking for, and we would have a triangle that had sides of 7, 8, and an angle that's 50 degrees, correct? But it turns out, would have been possible to make a segment that was 7 that goes this way, and then I would have had a completely different triangle, this one that I'm highlighting right now, that has sides of 8 and 7 and a 50-degree angle, non-included angle for those sides. Okay, so two different possible triangles that you can make. Now, the smaller of those two triangles, right here, the second one that I made, happens to be an obtuse triangle, and the larger of those two triangles happens to be an acute triangle, the way that I drew it right here. But the point is, When you're given two sides and a not-included angle measure, sometimes there's more than one possible triangle you can make that has those measurements, which makes solving an SSA triangle kind of a challenge. Now, there's some more background information you need here. So I've mentioned in class before, and you'll understand a little bit better right now, that the sine rule can lie to you. Now, let me explain what I mean by the sine rule can lie to you. Suppose that I told you that you're using the sine rule, and you figured out that the sine of some angle A is equal to 1/2. And I asked you to find out what that angle A is. Well, you ought to know, based on what we've done earlier in the chapter, that there's two different angles between 0 and 360 degrees whose sine is equal to 1/2. Angle A could be 30 degrees. And I'm just illustrating that in the unit circle over here that I've drawn, because it's possible for the sine of 30 degrees, the y-coordinate is 1/2, isn't it? But you also know that there's another angle that has that exact same sine measure, and the angle that has the exact same sine measure as 30-degree angle would be a 150-degree angle. Remember, supplementary angles have the same value of sine. So it's possible that angle A could be 150 degrees, right? This could be the angle that you're talking about as a sine of 1/2. There's a 150-degree angle. Its sine value is the same as the sine value for 30 degrees, right? Okay, now do this for me. Go ahead and type in on your calculator the sine inverse of 1/2. Well, what it's going to give to you is 30 degrees. Does that mean that a 150-degree angle does not have a sine that's equal to 1/2? Absolutely not. But here's the point that I'm trying to make, is that whenever you use the sine inverse function, it's always going to give you an acute angle. Actually, occasionally it can give you negative angles as well, but for our purposes right now, a sine inverse will always give you an acute angle. And so even if you're finding an angle that was supposed to be obtuse, what it would do is it would give you the acute angle that's the supplement of that obtuse angle. The point being, you can't always trust what the sine rule tells you, and that makes some things unclear whenever you're solving side-side angle triangles. Now, a little bit more background, and then we'll get into actually solving this ambiguous case. I've drawn here 4 different triangles where I've given you a certain type of angle for an angle A, and I want to know, based on the type of angle that A is, what would be the type of angle that you would get for angles B and C. Because I'm trying to help you determine under what circumstances it's possible for an unknown angle to be obtuse versus when it has to be acute. All right, so let's say you knew an angle in a triangle happened to be obtuse. What would you know about the other 2 angles? Well, a triangle can only have one obtuse angle, can't it? So in the situation where angle A is acute, you automatically know the angles B and C. In the situation where A is obtuse, you automatically know the angles B and C are acute. If ever you happen to have a side-side angle triangle and the angle you know is obtuse, you don't have to worry about the sine rule lying to you because the other angles have to be acute. Kind of similarly, in a right triangle, well, you can't have 2 right angles. You can't have a right angle and an obtuse angle within a single triangle. So if you know that angle A, the angle that's given to you, is a right angle, you again know that the other 2 angles have to be acute. However, if we're talking about angle A being an acute angle, then it's unclear what kind of angles B and C can be. All right? It's certainly possible that all the angles in a triangle are acute, isn't it? An equilateral triangle, for instance, every angle is 60 degrees. So one situation you could have if angle A is acute is that angles B and C are acute. But it's certainly possible that if angle A is acute, that you have one obtuse angle, or possibly a right angle, and one acute angle, right? So it's unclear whether the missing angles, when one angle that you know is acute, it's unclear whether the other ones are obtuse or acute or right. And the word ambiguous happens to mean unclear. Now, it just means it's not quite certain what the case is. Well, here's what we're going to be doing. We're going to be solving side-side angle triangles, and you're going to be told to find all the possible solutions of a triangle. And what you need to know right now is that it is going to be ambiguous sometimes whether a missing angle that you find is obtuse or acute. But I'm going to give you some pointers as we go through problems that are going to help you determine whether the angle could have two possible values or whether it's one possible value, or maybe it's possible that you can't even draw a triangle with the dimensions that are given to you. All right, pay careful attention to the way I draw the figures and to the way I make my conclusions here. It's going to be a longer video, but that's fine. You're going to understand what you need to. What we're going to do here is find all possible solutions to triangle ABC, and I've given you a situation where we've got an angle A that's 40 degrees, a side A that's 16, and a side B that's 21. Now, you'll kind of know you have a side-side angle situation anytime you know two sides at an angle, and the lowercase letter for one of the sides corresponds with the uppercase letter for one of the angles. That means those are opposite. All right, you're going to have two sides at a non-included angle. And the first thing I'd always like you to do with these is just go ahead and draw, so that it's possible to draw that 40-degree angle, go ahead and draw a side of indefinite length, okay, like I had in that other picture. And then choose a place for the vertex of the angle that you know. We're going to draw every one of these pictures the same way for right now, okay? And let's say that that's point A. And then we're going to make a 40-degree angle by drawing a side that's 21 units long. Now, we'll just say it's 21. We don't know whether it's 21 or not, right? But let's say that that is 21. Okay. Now, our first assumption is going to be that the other angles that we're going to make are going to be acute. So, what I'm going to want, well, at least the angle B is going to be acute. So, we're going to make a side A right now go something like that, and we'll say that that is 16. But as you saw earlier, maybe it's possible that that side A goes this way instead. Okay, so we're looking at this triangle might be a possibility, or this larger triangle might be the one that we're trying to get. Now I'm going to do a little bit of highlighting. Let's look at the larger triangle first. And let me do some more labeling of vertices here. If we're saying that this is side B, then that means that this could be angle B in that larger triangle that I've highlighted. Okay? And then that would mean that this is C. Now, ignore this 16 right here if you can. This one right here, we're just looking at the triangle that I highlighted. And I want to know what measurement would you be able to find next? Well, you know one angle and opposite side length. And then you know another side. The next measurement we could find with the sine rule would be the opposite angle to that side. We would be able to find angle B. And the way that we're going to do that is we're going to use the sine rule. We're going to say that the sine of B over its opposite side, 21, equals the sine of 40 degrees over its opposite side, 16. Now, we're going to get the sine of B by itself here. And I'm going to write it as a decimal because the decimal approximation is going to be very important for what we're trying to use here in this ambiguous case process. I'm multiplying both sides by 21, so I'm doing 21 times the sine of 40 and then divided by 16. You can do that as well on your calculator right now. Now, I won't go into too much specifics right now, but it's very good for you whenever you find out that the sine of an angle is somewhere between -1 and +1. The sine of an angle always has to be between -1 and +1. All right? If this had been greater than 1 or less than -1, we would have an impossible situation. You'll see that in one of the examples that we do later on. Now, if the sine of B is 0.844, then that means B would be approximately equal to the sine inverse of 0.844. And according to our earlier discussion, that's going to give us an acute angle, isn't it? Type that in and see what you get. All right, so in the scenario where we assume that angle B right here is an acute angle, angle B would have to be 57.6 degrees. All right. Now let's do this. I'd always like you to compare the measurements and see if they actually make sense. So we're going to use a little bit of logic regarding triangles. You know that if one angle of a triangle is smaller than another angle of a triangle, as A is less than B, then the side opposite angle A has to be less than the side opposite angle B. All right, so since 40 degrees is less than 57.1, that would mean 16 should be less than 21. And since that checks out, that means it is possible for sure for this angle here to be 57.6 degrees. Now, I'd always like you to go ahead, because I think it'll be easier to teach it this way, I'd always like you to go ahead and assume that it's possible for angle B to be obtuse as well. And if it's obtuse, it would be equal to 180 minus 57.6, right? Because you use supplements. And so the other possible angle measure for angle B is 122 degrees if you're rounding to three significant figures. All right, so that would be this situation. What if we had drawn the smaller triangle, and instead of this being the vertex of angle B, this was the vertex of angle B? All right, well, that should work if it's possible for this angle to be 122 degrees. Now, is it possible? Well, if it weren't possible, what you would have is a situation right now where if you added angles A and B together, they would exceed 180 degrees. It is possible, certainly, for this angle to be 122 degrees, because all that means is that the angle C right here would be, let's see, 162 subtracted from 180. That would make that 18 degrees, right? Okay, so in this case, there are two possible solutions. And those two solutions, one of them occurs when B is less than 90 degrees. The other one occurs when B is greater than 90 degrees. In other words, an acute and one obtuse solution. So let's look at if B is approximately 57.6. We would still have to solve the rest of the triangle, wouldn't we? If B is 57.6 and we're looking at the triangle that I highlighted earlier, then we would have to figure out the measure of angle C, and that would be 40 plus 57.6 taken away from 180. That's 82.4 degrees. Okay, so if angle B is 57.6, then C is approximately 82.4 degrees. These are the angle symbols there. And then we would have to make a proportion in order to find the value of side C. We would say that C over the sine of 82.4 is equal to, and let's use the A and angle A here, 16 over the sine of 40 degrees. And you'd find that C is approximately 24.7. Okay, so that's solution number one, we'll call it. Then there's solution number two. Why don't I just write that in blue, let's say. And solution number two would assume that angle B was an obtuse angle, and we said it would have to be 122 degrees in that case. So angle B, approximately 122 degrees. And then that would make angle C, we said earlier, approximately 18 degrees, right? And then in the case that angle C is 18 degrees and so forth, we would say that C over the sine of 18 degrees, talking about side C right there, is equal to 16 over the sine of 40. In which case, this third side C, well, it would be right there, wouldn't it? Would be approximately 7.69. I know that seems a little overwhelming right now, but you can see how it's possible to get two different solutions out of a single side-side angle triangle. Now let's look at another side-side angle triangle so you can see some other possibilities. All right, I got another angle and opposite side given to you, and then the third side, this is going to be another side-side angle triangle. Draw it the same way we did before. Go ahead and make your line of indefinite length here. Put a vertex for it, and it'll be angle B for this one. All right, and then we'll make the 40-degree angle, and it's going to be 9 units long. It has to be the C there, because again, the B, side B, has to be opposite from angle B, so it would be over here somewhere. So that's going to be 9. And then just go ahead and get accustomed to making two different triangles. And we're going to find out if both of them are possible, but let's go ahead and make this and this. Now keep in mind, this segment that's 9 units long is segment C. So in this case, here's one possible vertex for C. Here's another possible vertex for C. And those two segments are both B units long because in their respective triangles, they're the side that is opposite from angle B. So that's 12. That's 12. Okay. Now, just like before, I want to start off with the assumption that the angle opposite the given side here is an acute angle. So in this case, we were going to assume angle C is acute. And we're going to use that triangle then that I highlighted. And use the sine rule to find out what the measure of angle C is. So we're going to say the sine of angle C over 9 is equal to 12. Sorry, the sine of 40 degrees. I forgot to write that angle measure in there. I'll fix that in a moment. Over 12. All right, this angle here was 40 degrees. Okay, so then that will give us the sine of C is approximately 0.482. Again, it's good whenever the sine of an angle is between -1 and +1. That means it's possible to have an angle that would have that sine value. And then the sine inverse of 0.482 would give us the acute possibility for angle C. And that would be about 28.8 degrees. So under the assumption that angle C is acute, angle C would be 28.8 degrees. Now, I told you I'd always like you to operate at the beginning under the assumption that angle C, or the angle opposite the other side that you're given, is acute, or that it could be obtuse as well. So we're going to subtract 28.8 from 180 to find out what it would be if it was an obtuse angle. And you'd find that 151 degrees is the possibility if it's an obtuse angle. Now pay careful attention here. This is what I mentioned in the last example could happen, and now you can see it. The only possible obtuse angle measure for angle C is 151 degrees. But do you notice why that's not actually a possibility? We had a 40-degree angle in that triangle. We can't also have a 151-degree angle because that would exceed 90 degrees. So this is impossible. And just using a little bit of triangle logic, the triangle sum theorem, in fact, you were able to determine that it wasn't possible for it to be 151 degrees. And so what that tells us then is that this triangle has one solution only. And that solution is going to occur when angle C is 28.8 degrees. So everything else we do here is based on that assumption that angle C has to be 28.8 degrees in this problem. Now, let's find the third angle of the triangle then. Add the 40 and the 28.8 together, subtract from 180. All right, and it turns out the third angle would be about 111 degrees to 3 significant figures. Now, when you're writing out a solution, make sure you include all the unknown measurements originally from that solution, which in this case means you have to tell me what angle C is, and we said it would be about 28.8 degrees. And if this is B here and this is C there, that makes this angle A up here. And that was also unknown to us. In this instance, A would be about 111 degrees. And then we would have to, if that's angle A up there, this would be side A down here. We'd have to find out what the length of side A is, and that would be using the sine rule. A over the sine of 111 degrees would be equal to 12 over the sine of 140 degrees. No, not 140, just 40. And that would yield the result that side A is approximately 17.4, whatever the units happen to be. Okay, so you've seen an example where there were two possible solutions. You saw an example where there was one solution, and you knew there was one solution because had angle C been obtuse, the triangle sum theorem would have been invalidated. Now, we're going to look at one more possibility here. I've gone back to angle A, side A. Those are opposite from one another. and then side B. So draw the same picture again. I won't explain it this time, I'll just do it. Alright, so there it is with both possible triangles drawn. And I knew, of course, this would be angle B down there because this was side B up here. I knew side A had to go over there because where angle A was, right? Alright, so I did explain the picture a little bit. Now, let's go ahead and go through and work with that triangle where we're assuming that angle B is an acute triangle. So, this one right there. And use the sine rule, figure out what angle B would have to measure then. The sine of angle B over 30 is equal to the ratio between the sine of 40 degrees and 18. And if you figure out what the sine of angle B is, you'll see that it's about 1.07. Now, in each of the previous examples, I said it's a great thing when the sine of an angle is between -1 and +1. It's not a good thing. Well, maybe it is in a sense. We'll get to that in a moment. But it's not supposed to happen where the sine of an angle is greater than 1 or less than -1. Now, what I want you to go ahead and do is type in the sine inverse of 1.07. And what you're finding is that your calculator gives you an error when you do that. Now, let me go back to the unit circle really quick. I'm going to go back a few slides and explain that to you. Remember that this is a unit circle, right? The radius here is 1, meaning, and the sine value goes along with the y coordinate. Well, the highest the y coordinate can get to is +1, isn't it? If it went past 1, you'd be outside of the unit circle. All right? Sine of an angle can never be greater than 1. Similarly, it can never be less than -1 because, well, the radius of the unit circle is again 1, and so you'd be saying the sine of the angle is greater than the radius. Not possible. So, if ever you get a situation where you get the sine of an angle is 1.07, that means it's impossible to make a triangle that has those measurements. All right? This is impossible. Which means that there are no solutions, acute or obtuse or right, for this particular situation. Now, believe it or not, I know the length of this video is longer than I like, but we've done a real cursory inspection of the ambiguous case, and I've shown you how to recognize when you have 1 solutions, 2 solutions, or no solutions, as much as IB is going to care about. Far more to it, but you should be good as long as you have a basic understanding of this stuff. I'll see you in class. We'll talk more about it later.